Welcome to the presentation of our tool demo paper on automated unit test generation for Python. My name is Stefan Lukaschik, and this work was done under the supervision of Professor Gordon Fraser at the University of Passau in Germany. Assume you're working on a Python project and you have an existing code base. Furthermore, assume this code base might be large and complex, and your time is, of course, very limited. Now, your manager asks you to come up with test cases for the project, as there have been none yet, such as the one that we can see here. So, what can you do? Well, of course, you can start and bang out the test cases of the rock manually. This is often considered tedious, repetitive, and time consuming, and since the project is large and you're not having too much time available, this might not be the solution that you want to aim for. So actually you want to aim for a different solution, and since we're all software engineers who love to not get our fingers dirty, but instead have some automated tooling, you want to run an automated solution, of course, an automated test generation framework that removes some of the burdens from you and creates you the required tests automatically. Automizing this process was one of the motivations when we started building Pynguin, an automated unit test generation tool for Python. We introduced Pynguin in our SSBSE 2020 paper entitled Automated Test Generation for Python. Pynguin is an open source tool written in Python. Its source code is available from GitHub, and it can easily be installed with the pip tool, which we will see later on in the demo. In this presentation, I'm going to give you some insights into Pynguin's internal architecture. I'll furthermore show you how to install Pynguin and how to run it. And finally, I will give you a quick insight into some preliminary evaluation results. Without further ado, we now want to look on how Pynguin is working inside, on how the inside are built. For that, we start with a module, usually a module containing Python source code. So we will come back to that file later in the demo, so its content does not matter now. And in the end, we want Pynguin to emit test cases in further Python modules. We will also come back to these results later, so we don't care what is actually inside that file now. So in order to come from the input source code to the test cases, Pynguin is divided in several stages, which allows extension and modification and also changing of behavior here easily. The first stage is called analysis, and it analyzes the given module and it extracts information from it, among others, about function, classes, and methods that are defined in the module. This information is incorporated in the so-called test cluster, which combines all the extracted information and basically serves the test generation tool then with information on what callables, what functions, methods, and classes are there that can be used to generate the test cases for which should be called. Furthermore, since most modules are not standalone, but depend on some other code, we also analyze, of course, the context of the module, that is the module it imports. From there, we extract information such as classes that are defined there to use these as further input types during test generation. And we also include this information that we gain from the context into our test cluster. So based on this test cluster, now Pynguin starts generating test cases. That is, inputs for the classes, functions, and methods in the given module under test. For that, we can utilize several well-established test generation algorithms, for example, Dynamoser or Holesute. Each generated test case gets executed to see how the program under test behaves with the newly generated sequence of statements that calls it. So a test case is basically up to here a sequence of statements that calls some functions and methods and classes of the module under test. Some of these inputs that we generate here might run successful executions. Others might crash the program under test. In any case, we are interested in the achieved coverage and use this information about covered statements and branches to further guide the test case generation. So currently, Pynguin supports combinations of statement and branch coverage that it can use to optimize the test cases for, and the target is, of course, to yield test cases with high coverage. This process runs in a loop, and some stopping criteria are terminating this loop. For example, a stopping criterion can be a timeout, or of course, full coverage of the module under test, because when we have covered everything, we have reached our goal of achieving high coverage. After stopping this test case generation, the test cases still only contain sequences of statements that execute the code of the module under test. This does, however, not provide good test cases because we still miss checks for the values the program under test emits, so-called assertions. The assertion generation aims to generate regression assertions that are assertions that check for the behavior that is currently implemented in the module under test. We use a mutation-based approach to minimize the number of these generated assertions. We generate mutants of the original program under test and execute the newly generated test cases together with their assertions against these mutants. We keep the assertions for those values that change in the mutated versions of the program under test to kill these mutants with our generated test cases. Assertions for values that do not change are discarded, as this heuristic assumes that those are not relevant anymore and they do not influence whether we can kill further mutants here. And finally, we export the test cases to the test module. So that's about the abstract view on how Pynguin is built and structured, but I now want to show you how to run the tool. And for that, I will install it, show you how to run it and how its input and output looks like. So let's directly dig into this. For the demo, I want to use a small class implementing a queue for ints, which is a very basic toy example. It could be taken from a data structure 101 class. It's a very simple thing. So this class queue basically has a maximum size. It has some data that it stores and some other fields that used for internal handlings. It provides a couple of methods, for example, an empty or a full method to check whether the queue is empty or full respectively. And of course, it provides two further methods, one to enqueue values into the queue and one to dequeue values from the queue. So as said, this is quite simple, but we will use that, and I will show you using this class how to use Pynguin to generate tests for this class. For that, we will need to install Pynguin in the first place. And since it's a Python program, it's highly recommended to use a virtual environment to install it inside this virtual environment and not system-wide. The reason for that is if you install too many dependencies or programs system-wide, this will fill up your public class path for your global Python interpreter, which can easily cause conflicts and dependencies and things that you cannot easily handle then. So the recommended way is to use virtual environments, which are basically dedicated interpreter environments for running a specific tool or program with isolated dependencies. So I will do this by simply typing virtual env command here, and I will create a virtual environment based on the Python 3.10 interpreter on my system. And that's basically it. That takes a couple of seconds and creates a virtual environment folder, which is basically a copy of the public Python class path into a separate environment. So to use this virtual environment that we just created, I need to source it into my shell, and that basically the activate scripts does all the things, setting paths correctly, that my interpreter that is used now will be the one from the virtual environment. And now I can install Pynguin, and I will do this in the standard way of installing Python packages by simply typing pip install and the package name, in this case Pynguin. When I hit the enter button, it will pull in all the necessary dependencies. In my case, they are already cached on the systems because I've done this before. If not, it will download the dependencies, and after a couple of seconds, this usually is installed and the process finished, and we get back to the shell prompt, which we right now got. And from there, I can directly start using Pynguin by typing Pynguin on the command line. And well, we see a warning here that we should set some environment variable. Let me elaborate on that for a second. The reason why we do this is Pynguin will execute the code under tests, so the code that it generates tests for, and this can, of course, potentially cause harm to your system. Imagine a module that modifies or deletes files from your file system. So if you're just creating tests for that, this might cause trouble when you're missing files afterwards. So in order to make users aware of it, we force them to set this environment variable um, with which they tell Pynguin, hey, I'm aware of the risk, I know what I'm doing here, and I will not accidentally break my system. So I will now set this environment variable, and the easiest way on a Unix system is to use the export command. Then it's set for the current session. Actually, the value doesn't matter that I set here behind the equal sign. So I could use some arbitrary thing. Important is that the variable is defined, which I now do. And when I run Pynguin again, the command, I will get a different output. A very long output, to be honest. That's an output that shows all the parameters that Pynguin has, together with the documentation command. And there are a lot of them, and we will not utilize all of them. I will not go into the details of most of them, but just stick to the very basic ones that are necessary to actually execute Pynguin. So in order to do that, I start again by typing Pynguin and then set variables to values that I need. So I want to generate tests for the module Q example that we've just seen. So what I do is I set the variable module name, the parameter module name, to the name of the module. So this was Q example without the suffix .py. Then what I also need to specify and tell Pynguin is where is this module actually stored on my hard disk. So I use the project path parameter for that and tell it it's in the current path. If it's not in the current path, of course, you have to set something different here. You can also use an absolute path or relative path. But since it's in the same directory, I can just use the dot as an abbreviation for that. And the third thing that I have to set here is a parameter that tells Pynguin where to store the output, which is called output path, and I want to have the output also in the same directory. These three parameters are the required and mandatory parameters that you have to set in order to use Pynguin, and that would be enough to run the tool. For this demo, however, I decided to set one parameter further, which is called seed, and set it to a predefined value that I've already tried out and that I just copy in here. This seed is the seed for the random number generator that is used inside Pynguin for various stuff that is based on random numbers. And this seed guarantees me now that we have a quite fast convergence of the test generation and do not have to wait for too long. If you do not set it, it will use the current timestamp as a seed, which will be different for each execution, of course. But if you want to have repetitive and repeatable executions, then we recommend to set the seed. One more parameter I'm going to set, which is the -v parameter, to get a more verbose output. So the default version or the default behavior is that Pynguin won't print any output, which is fine if you run it, for example, on a computing machine for running experiments for your research. But if you do it like for a demo or want to have a better insight, then you want to have some output. And that's why I set the verbose mode, which I could increase by adding another V, by the way. I'm setting this verbose mode that we can actually see what's happening here. So when I hit the enter button now, Pynguin starts generating tests and yields some lines of output here. I'll just let it run and come back to the lines after it has finished, which is now, and tell you a bit about what is going on there. So we start again up where we started the test generation. It tells us which seed we used, so this is the same that we used over there. Pynguin collected constants from the subject under test, which is the test cluster generation. It uses the dynamoser algorithm and initiated a couple of fitness functions for this algorithm. It also tells us which further operators it uses for the algorithm for controlling whether we have set things correctly. And it also tells us that we have a default timeout of 600 seconds, meaning after this time the test generation will stop. Then it starts to actually generate tests down here with an initial population where the coverage is also already measured with almost 79% of covered branches. In this case, we are measuring branch coverage of covered branches in the program. Since this is not the full coverage, Pynguin or the dynamoser algorithm will now try to improve this population. And when we look down over the iterations that follow here until iteration number 8, we see that it actually was able to do so and that it yields 100% coverage. This is, as said before, sufficient that we can stop early and not wait for all the 600 seconds. So we have covered all the branches, all the targets in the module, and can now stop the test generation and continue to build the assertions for the program. For that, we set up a mutation controller, as we call it, and generate the mutants out of the original Q module that we have seen before. And the used mutation tooling generated 31 of these mutants. It then executes the tests on each of these 31 mutants and kills a couple of them, and some others might survive, which is not documented in the output here since it's not that interesting. In the end, what we see is that Pynguin exports a couple of test cases to 2 files. Let me start with the latter file, the test queue example failing file first. These tests are called failing tests because we actually do not know how to handle these properly. So what happens there when you execute the code with these inputs that are in there, there will be an exception raised. So we do not know, since there's no concept of checked and unchecked exceptions like you might know from Java, for example. Since this concept does not exist in Python, we do not know how to handle those, and so we put it into a module of so-called failing test cases and let then the user of Pynguin decide on how to continue with that. The other module containing 3 test cases, now those are the successful test cases, those are successful executions of the program under test, and we will have a look at those now. So I've just opened this before to avoid any loading time. The module will look like this. Basically, it imports the code under test here and names it module _0 for as an alias name to reference this. And then it defines a couple of test cases, 3 as we have seen here. And each of these test cases consists of statements that set up variables, statements that now call the subject under test, in this case the constructor, and assertions that check for several properties, whether they are met or whether they are hold. So, for example, if we use or if we set different values, then the assertions also change. Like we can see here with the len assertion in the first place, and for the second queue that's here, it has a different value. And the other tests are similar and alike, where we store values, where we dequeue values from the queue, and so on. So that's basically how you can use Pynguin in its default setting. Of course, you can also add various arguments to it if you want, and configure its behavior in more detail. So one example I want to quickly show you is using a different algorithm. And for that, I'm using the MIO algorithm as an example. I could use any other that is included, like the standard Moser or whole suite approach. I'm using MIO for this example and adjust the parameter algorithm in MIO and let it run again, and we see the behavior is now different. In this case, There are many generations produced, but the coverage does not increase, so it was not able to find any successful modification of the population um, that is actually here. So this will run for a couple of seconds more, and just to not spill the time and waiting for that, let's continue with our results that we have gained with Pynguin so far. We've done a preliminary evaluation for this work using 118 Python modules that we also used in previous work. We've used Pynguin version 0.17.0 for 30 times on each module and each configuration to minimize the influence of randomness. Furthermore, we set the time available for test generation to 600 seconds, which is an established time limit in the related literature. Here I only show you the best and worst performing test generation algorithms in this experiment. Please have a look at our paper for the numbers on the other test generation algorithms that are implemented in Pynguin. The plot you can see shows the average coverage development over all modules over the generation time of 600 seconds. Best performing on our 118 modules in this experiment is the Dynamoser algorithm, depicted in blue here, which reaches an average coverage of 68.0% overall runs. The algorithm yielding the least coverage in this experiment is our random algorithm, which is plotted in green here. It yields an average coverage of 63.5% after the 600-second runtime. As I've already mentioned, Pynguin is open source software available from GitHub. You can find more information about it, its documentation, links to the repository and to already published paper on the tool's website pynguin.eu. In this presentation, I've presented Pynguin to you, our automated unit test generation for Python. I've shared to you the insights on how Pynguin works. I've shown you how to install and run Pynguin in order to generate tests for your own code. Pynguin is an open source software available from GitHub, and you can find all the information about the tool from the tool's website, pynguin.eu. We would like to highly encourage you to try out Pynguin on your own projects and report back your feedback and experience. Thank you for your interest in Pynguin and in this presentation.